Before we proceed, let's do a quick review. The four main characteristics of SDN that we discussed are flow-based generalized forwarding, separation of data and control planes, control plane functions being external to switches, and programmability of network control applications. We previously discussed the generalized forwarding and the separation of control and data planes. This allows the centralized remote controller to run routing algorithms in a centralized way and propagate the generalized forwarding tables into the data plane devices. In software-defined networking, in addition to remote calculation of routes that are written in generalized forwarding tables, through protocols like OpenFlow, control plane functions that run in remote servers make it possible to implement programs with finer-grained network control. An example of such external functions is traffic engineering, implemented as an application, controlling the traffic in the flow granularity. In that sense, SDN can be divided into three components: data plane switches, SDN Controller, and network control applications. Therefore, the SDN control plane spans over two components: the SDN Controller and the SDN Network Controller applications. The data plane switches are simple commodity switches implementing generalized data plane forwarding in hardware. The flow table, which is computed in the SDN Controller, is to be communicated and installed at these devices by the controller. So, at this level, the role of the controller is to provide the communication layer to these devices. This happens through southbound interface. OpenFlow is a protocol that we will discuss that serves this purpose: communication between the devices and the controller. SDN Controller is like a network operating system. It maintains network state information. It interacts with network control applications above it using northbound interface and with network switches below it using southbound interface. This logically centralized system is actually implemented as a distributed system. This decision is for achieving and maintaining performance, scalability, fault tolerance, and robustness. Controllers like OpenDaylight and ONOS, that we will discuss briefly, have placed emphasis on architecting a logically centralized but physically distributed controller that can scale services with high availability. Control of the network in a logically centralized way needs having information about the network to be controlled. This information is collected from the devices using southbound interface. The collection of information making the state of the network could be used by northbound applications for decision making and implementing specific functions. Network control applications sit on top of SDN Controller and communicate with it through northbound interface. They are the brains of the control. They implement control functions using lower level services. The functions implemented through these applications can include routing, access control, load balancing, firewall, SD-WAN, or other network functions. These applications are not tied to a specific hardware. They are not tied to a specific server or controller either. They could be provided by different developers or third-party vendors. Putting the components of SDN Controller together, we can summarize the three main roles for it. First, providing northbound interface to network control applications. Applications can register to be notified when a state change happens so that they can respond to events. Different types of APIs can be used for northbound interface. Second, network-wide state management. Link state information, host information, switch information, statistics, and monitoring. All of them ultimately leading to flow table calculations to be propagated to the devices. And third, providing southbound interface to control devices.